Alright, so today we will be doing this linked list problem. And this linked list problem is actually a little bit similar to that rainwater problem. Since its basic logic is that you need to compare the highest node. I mean the node with the largest value. So we call it just for simplicity, we just call it the highest node. The highest node on its right hand side. So here's the problem: is that in a linked list we want to delete some nodes, and the nodes that is going to be deleted is the nodes that with the node on its right hand side, and that is larger than the value of this node. For instance, let's see, like in this case, this 5 is not gonna be deleted since all the nodes on its right hand side has value smaller than this 5, but this 2 is going to be deleted since we can see that on its right hand side the node, for instance, this 3 is larger than it, so it's gonna be deleted. And let's see, like for instance, this 2, however, won't be deleted since on its right hand side the nodes are just smaller than it. Alright, so for this problem, we're since whether the node is going to be deleted is determined by the nodes or the node on its right hand side. So by intuition, we just want to start on the right hand side. We want to start from this side. However, since this is a single linked list, we are actually not able to do so. So we probably need to go to the last node. Surely we can just use a while loop to just go from the head to the last node, but this won't help us much since later on we definitely want to go back. However, since all the pointers are pointing to the right, then it's just quite hard for us to go from the last node back to the first node. So what we're going to do is that we first want to reverse. So we first want to reverse the linked list. We want to kind of just start from the right hand side. We want to make the right hand side as the new head, and we want to change the directions of all the pointers, all the links, right? So this way we can just go from this last one to this first 5. All right, so far so good. And then we actually want so since we are comparing the nodes, if we just have one reference, just one pointer, one variable, it's not gonna be enough. So by the first glance, I think it's proper to use 2 pointers. So for instance, the one pointer, the main pointer, is just going from this 1 to this 5, going this way, and the main pointer is the points to the node that we are currently checking. And after checking this node, we do some operation depending on its value and the result of the comparison, and then we just move to the next, move this way, and until we finish checking the last one, the head of the original node, right? And simultaneously we need another pointer. Let's denote it as yellow. So we need another pointer. The second pointer should keep track of the largest one ever we have met. So we want to know what's the largest one on the right hand side, just the one that we have checked since the beginning of the checking process. And this way we can just compare the one pointed by the blue pointer, the current one that we are doing some operations. We want to compare its value with the max, the highest value we have ever met, which is pointed by the yellow pointer, I mean the second pointer. And this way we can decide whether we want to delete it or not. So let's see we have already done the reversion, and now clearly that the last node won't be deleted. And just it cannot be deleted since there's nothing on its right hand side, so it's there. So we can actually start our blue pointer from the second last one, before the reversion, and after reversion just the second element. So we started with this 2, and then we want to compare it with the largest one on its right hand side. And since initially there's only one node on its right hand side, so we can just see the yellow pointer is now pointing to the largest one. We want to compare their values, and now we can see that the 2 is indeed larger than the 1. Then this means that we want to include this 2 in the final answer, the final linked list that we want to return. And also we want to move the main pointer, the blue pointer, to the next element, which is this 3. We want to keep checking the next one. And how are we going to add this 2 to the result? We cannot just do, like, for instance, we call this yellow pointer. We cannot just do yellow.next equal to this 2, since this way, when we are returning, for instance, when we are returning the yellow pointer, the initial yellow pointer, the order won't be correct, since in the final result this 2 should be before this 1, right? The final result here should be 5 3 3 2 1, not just, so this 2 should come before that 1. So instead of just this 1 just now currently pointed by the yellow pointer, yellow dot next equals to 2, we want actually this 2, this node dot next to be the one, to be the last node that is currently pointed by our yellow pointer, right? So be careful of the order here, be careful of the direction of the link here. So with this purpose, we actually want to say that before moving the current, the blue pointer from 2 to 3, before doing so, we want to say that the node 2 currently pointed by the blue pointer, we want to say that this 2 dot next equal to the one pointed by the yellow pointer, the 1, right? However, we can see if we just directly do so, we just make 2 pointing to this 1, then we may get another issue, is that here's a circle in the linked list. Since after reversion, 1 is pointing to this 2. So note that initially we want to break this link. So before the process, we want to break this link. We want to see that this one is so we want to set that 1, or the one just pointed by the yellow pointer, right? The yellow pointer dot next equals to null. So we want to break this link before the process, and we should do the same thing just while we are moving from this 2 to this 3. So we want to, so now know that we want to first update our the previous pointer, the yellow pointer. We want to move the yellow pointer from this 1 to this 2, right? And we have already said that 2 is pointing to 1, and then we want to move the blue pointer from 2 to 3, and simultaneously we want to also break the link between the 2 and the 3, just as we did before, just break the link between 2 and 1. We want always to make sure that the node pointed by the yellow pointer dot next is null. We want to break that link. All right, and let's see, what if we don't want to include that node in the final result? For instance, now our blue pointer is now on this 1, and our yellow pointer is now on this 3, and we know that value of the node pointed by the blue pointer is smaller than the value of the pointer pointed by the yellow pointer. 1 is smaller than 3, right? And then we just want to see, so we do not want to include this result in the final result. We do not want to include this node, so we just directly move the blue pointer forward. We just move it to the next element, next 3, and we just kind of skipped this one. And note that since this link has already been broken, before we move the just when we move from 3 to this, move from this 3 to this one, this link is gone, and now our blue pointer is pointing to this 3. Now actually we do not have any method to obtain this node, this one. So we can see actually this one is gone, and later on the garbage collector will just release the space and completely delete this node. All right, and we keep on doing this process until we have checked all the nodes. We have checked this 5, and later on our blue pointer is pointing to null. So we just end the process, and then we just return the yellow pointer as the head of the final result in linked list. So let's do the coding. All right. So first we want to reverse our linked list, which is just quite easy. I don't want to say much about the process of reversing the linked list. So okay, so here the linked list has already been reversed, and now the new head is gonna be pre. So note that our yellow pointer starts with the new head, while our blue pointer starts with the second one in the reversed linked list. So we want to say that list node. So to make it more intuitive, so it's not a good naming approach, but just for clarification and for easiness of understanding, we just say this node blue, so the blue pointer, right? But note that in real world applications, when you are just doing your coding, not for explaining the algorithm, please just give it a proper name. And we want to break the link, so pre.next equals to null, and now while blue is not null, so we just want to check if blue.value is smaller than yellow.value. If so, if blue.value is larger than or equal to, so if so, we just want to include it in our final result. So what we are going to do is that we want to say like blue.next is equal to yellow. So this way we are just making this 2 pointing to 1, so 2 pointing to 1. Blue.next is equal to yellow, and then yellow is equal to blue. Yellow is equal to blue. And also we want to see that blue is equal to blue.next, so we move the pointer forward. We move from this 2 to this 3, so blue is equal to blue.next. And also we want to break the link between this 2 and this 3, right? So yellow.next is equal to null. And if the node else, if the value of the blue is smaller than the value of the yellow, then we do not want to include it in the results, so we just simply do the blue equals to blue.next. All right, and finally we can just return yellow as the head of our solution, the resultant list. So let's run the test. Okay, so we get an error here. Wait. Oh, sorry. We here the condition should be current since we are just operating on the current, not the head. Wait, so here's a problem here. Let me see how to fix it. Alright, here's the problem. Since this line is not actually moving to the next one that we should be checking on, since know that we have done blue.next equals to yellow before that. So actually before doing so, we just need to kind of use the temp to store the real next, just the node on the left hand side. So here we want to, for instance, we are moving from this 2 to this 3. We want to first store this 3, and then we change the pointer. We make this 2 pointing to this one, and later on we just use the pre-store this 3 to update the value of the blue pointer, right? So equals to temp, and now it should work out well. Wait, it's still not correct. Let me check. Alright, this one is not working properly, since what we want to break is the link between the 2 and 3, not the link between 2 and 1. If we do yellow.next equals to null in the very end, we're actually breaking the link between 2 and 1 instead of breaking the link between 2 and 3. So we should do it before, just right after we have stored that 3. Right, so yeah, and actually it's not just quite necessary, right? Since whatever we're just doing blue.next equals to yellow in the next step, we're kind of just for instance, there's originally a pointer just pointing from 2 to this 3. We're actually just changing this pointer just directly to like 2 pointing to 1. So yeah, this step is actually useless. Sorry, that's silly. I just made a silly mistake by the very first step, the reversion algorithm here. I should be doing like current equals to this temp, not just current equals to current.next, since current.next is already set to be the pre. Right, so here everything seems to work well, and let's see the final result. Right, we're just kind of fast. It's one of the best solutions, and let's analyze the time complexity of this algorithm. So we're doing the reversion, and the reversion is O(n), and then we are just kind of going from the last element to the first element, the last node to first node. So here this while loop is also O(n). So n plus n is 2n, and 2n is just the same thing as the just as O(n). So the time complexity is O(n). And talking about the space complexity, we're just using a finite number of nodes to help us do so. Just like more pointers, some pointers and some just temporary holders. So the space complexity is O1. Alright, so here's this problem. See you soon.